So let's start with some of the block diagrams that we wanted to have. We have something like a block diagram which helps us understand what are the different components that are present. And in the NMR spectrometer, you have three individual components, as you are able to see. One will be in the magnet, as written here. The other will be the RF circuitry and the receiver circuitry. These two would be a part of something called a console. And this is the computer with which we end up interacting when you're actually in the NMR center and trying to set up your experiments. And there are different components to each one of this. So I'll go over one by one. So this is, as I said, this is the computer in which you will start typing commands. I'll try to show the software we end up using. If you're using a Bruker spectrometer, the software is called the TopSpin software. You'll be using the TopSpin software giving commands, which will then end up interacting with various hardware that are present in the console and therefore help you get whatever you want from the magnet and the probe. Let's start with the magnet here. There are different components in the magnet. The main components are listed here. The most important component of the magnet is called the probe. Although we list it under magnet, this is something that is detachable. Generally, probes are replaceable. You can have different types of probes. The probe is one where your NMR sample ends up sitting in. Okay, so let's assume this is your NMR sample. When you throw it in, it actually ends up sitting in the probe. The probe is one where you end up receiving signal for whichever nuclei that you want to see. This once again forms the heart of the NMR spectrometer, where the components in this critically decide which experiments are feasible for you and which are not. Then comes the Shim coils. The Shim coils are one can imagine these are electromagnets around the sample, and these help homogenize the magnetic field. Okay. Of course, this is important here because we did not spend much time talking about the magnet. The B naught that you end up talking about is other most important component of this entire part, where the B naught helps you achieve a certain magnetic field strength. And this is achieved by the use of superconducting coils. Superconducting coils are one where when you reduce the temperature, they have almost zero resistance, resulting in the fact that you could have the highest of magnetic fields that could be obtained. Nowadays, there is a serious quest for people trying to achieve superconductivity at room temperature, and if it does happen, NMR would benefit significantly from it. The Shim coils are in addition to this B naught, where the B naught helps you get the largest of the magnetic fields you could get. The Shim coils around it would help you homogenize the magnetic field. If you remember, magnetic lines of force have to be as parallel as they could be, not something like this. So this would constitute an inhomogeneous B naught, while this constitutes a homogeneous B naught. The Shim coils help you achieve this target of homogenizing the magnetic field. So therefore, you get very well resolved resonances. Therefore, you'll be able to do NMR at a very high resolution. This is the next component we generally attribute it as the lock. These are steps that you will also do in an NMR experiment. Hopefully, you will have a demonstration as we go forward. What this ends up doing is to use a nucleus that we don't end up exploiting most often and fixes the field and frequency with respect to each other. For instance, at a given B naught, you would know what will be the omega naught for deuterium. So therefore, which is going to be minus gamma D times B naught. So once you have a B naught and a gamma D is fixed for a given nuclei, the omega naught for deuterium is fixed. However, what ends up happening is that the B naught might end up drifting over a period of time. What do I mean by drifting? You have to write 11.7 followed by several decimals here. The last decimal could slowly start changing. Let's say 6th decimal could slowly start changing. So what that ends up resulting in will be loss of resolution. Once again, you will start to get broad peaks just because your B naught is not homogeneous. I mean, it's not constant as a function of time. So therefore, what we end up doing here is that we have an internal circuitry which keeps checking for how much ever the B naught drifts, the frequency for the deuterium is corrected. So for instance, whatever changes come up here, there is an internal circuitry that gives current to make up for the changes that come, so as to ensure that as you run the experiment, the B naught is more or less kept constant. So this process is what is called locking. In fact, it's called field frequency locking. So therefore, if you are able to see here, all these components put together ensure that you have a high magnetic field, and in the presence of a high magnetic field, it's homogeneous. And on top of it, as a function of time, the magnetic field does not drift. Under this context, your sample that sits in the probe can actually be characterized. So the next component that we'll be looking at here would be the RF component. The RF component is important because the computer, wherever you end up typing some commands, will be sent forward. For instance, in the computer that you have, you might clearly indicate you have a 90-degree Y phase pulse with an acquisition. But remember, this has to be translated back in a way where the probe can understand. That is what is being achieved by this RF circuitry. So in this case, what you end up doing is that you write in a language that you understand in this computer, and that gets transferred to this pulse programmer, where whatever language you ended up writing here gets converted in language that the other electronics can understand. And you start applying the omega RF in this place actually. Remember, we had this cos of omega RF t plus phi. Of course, the phi we just set as the Y phase. And of course, there's also a B1 that you have up front. Not able to write here. So yeah, you have a B1 up front. The B1 is what is deciding whether it's a 90-degree pulse or whatever flip angle it is. Well, the omega RF gets added up by this frequency synthesizer. We will see why it is coming back later on in the receiver as in a little while. So after you have that, you also have the RF transmitter, which is what ends up interacting with the probe. Once you apply the sequence of commands which you wanted to do, it gets transferred to the probe. So now, therefore, your sample ends up experiencing the whatever changes that you want to do, whatever perturbations you want to do, however you wanted to acquire it, are all therefore transmitted to the probe. After having done that, you applied your pulse, and the signal that ends up coming, which is your free induction decay, so we can try to say this is the pulse, the free induction decay will be obtained by the receiver. And the receiver also has multiple components in it. One of the main components here is called a pre-amplifier. We will at least learn about the pre-amplifier again in a little while. What this does is that the main difference between the pulse and the signal that you obtain is that the pulse is of very high power. However, the signal that you get is of very low power. I mean, in terms of current, you can think of measuring currents in milliamps. And you can think of current here as an amps. So therefore, what will end up happening, after you apply the pulse, you turn off for a little while and then open this up so that you don't get overwhelmed by the pulse that you ended up applying. Remember, after you apply the pulse, it doesn't immediately die. It also has its own time to not be present anymore. So therefore, that's called the dead time, where transmitter is off, so is the receiver, both are turned off. But after that, you turn it on so that you can acquire a free induction decay. Since the signal is of very low intensity, the pre-amplifier that is present increases signal as much as possible so as to improve something called dynamic range. Let's quickly talk about what is dynamic range. Dynamic range is one where, let's say you have a signal. Remember, you're going to have sample that has a lot of water. You're talking about 110 millimolar of H plus ions that are going to be present. Let's say the protein that you're talking about is present at 1 millimolar. So therefore, what ends up happening, the huge difference between the signal from water and the protein is going to be like 10 power 5 orders of magnitude different. So therefore, what we end up doing is to kill water as much as possible so that we can amplify the signal that we get. Even within the protein, if you are able to imagine, CH, CH2, CH3, you would see that CH3 is more intense than CH because you have 3 protons that are present. So therefore, what will end up happening, you will have a mixture of strong and weak signals that are present. So therefore, the range of signals that you get would go from weak to strong. Now, if you're only getting the strong signals, it could happen that you will never be able to observe any weak signals. On the other hand, if you are able to observe, if you're only observing the weak signals, the strong signals could be out of detection. So therefore, you have to carefully manage the range within which you will be able to capture both the weak and strong signals, and this is what is termed as dynamic range. The pre-amplifier helps you keep an appropriate dynamic range so as to ensure the weak and the strong peaks are kept within spectrum. If you use way too high a concentration, the signal ends up going outside the detector. You won't be able to see. So that could happen when you're setting up the experiment only to see weak signals. But the problem will be the strong signals will overwhelm the detector that you cannot see them anymore. So this is an important aspect in almost every spectroscopy, and NMR is not any different from that. So now let's get to the next component of it, which is called the phase sensitive detector. In here, I would like to allude to the fact of Fourier transformation, where you guys were able to see e power I omega it gave you a signal at capital omega I and no signal at minus omega I. The reason why I kept on writing both sides is to show the fact that you will only get a signal at plus omega, and this aspect is called frequency discrimination. So this means that you should be able to discriminate plus omega I from minus omega I. If you are able to plot it, you will realize that in some cases you might not be able to distinguish it. So frequency discrimination plays an important part of it, which is why if you are only obtaining the cos omega it part of the signal, you will actually get a signal both in plus omega I and minus omega I. So this is an important aspect. So this frequency discrimination is done by the phase sensitive detector. So what does that mean? You not only collect the cos signal, but you also collect the sine signal, which is what you get as e power I omega t, and therefore you're going to have a signal at plus omega I like this and minus omega I like this. So therefore, when you sum up these two, you're going to get no signal at minus omega I and only a signal at plus omega I. So this is a very important aspect where the omega RF that you had put in is actually subtracted from it. Remember, your signal is within a spectral width, and wherever your carrier was, you switched it from the spectral width plus omega RF. So you just subtract the omega RF, which is why this feedback is required depending upon how much ever you added. You subtract that to get the spectrum within the range that you have. And the audio filters are the next series of ones which help you cut any signal that comes outside the range that you want to see. This is important because NMR is a very sensitive technique. So therefore, these bandpass audio filters would help you cut any signal or even noise that ends up coming outside the range that you would like to see. The last component that's extremely crucial is called the analog to digital converter. As we have been drawing all the time, we have been drawing the FID as though it's a continuous function, right? So this is actually called the analog function. Unfortunately, we cannot determine every point on it. So therefore, what we do, we discretize it, meaning that we get a bunch of points. We'll discuss more about it as we go forward. Okay, so this component ends up converting your analog to a digital signal. So if you don't end up carefully managing your gain for the spectrometer, the strong signals will result in something called ADC overflow, which means that you have so much signal that the ADC is not able to convert. So let's say this is the range of ADC converter. You're going to have signals. If you have signals that are above this, it's going to throw an error that ends up coming. Now, therefore, this discretized signal is then given to the computer, where once again we Fourier transform to take a look at the spectrum. So now let's go to the next component, which is the magnet. Once again, as I said, I'm taking all the pictures from this Kavanagh textbook because they look beautiful. So if you go to an NMR center, what you're going to see is something of this sort. So what you see here is actually probably this one of the earliest 900 megahertz spectrometers. And if you're able to see the size of a human being there, the magnet that you're talking about is significantly huge. These are the legs of the spectrometer. So there's also one more leg which you're not able to see. Okay, so that's how big an NMR spectrometer could look. So this is a reasonably sized magnet. And what you see here is 700 megahertz spectrometer. And this is something called a cryo platform. We will come in a moment. The probe will be right below the spectrometer. The sample will be inserted from the top. You see how small the spectrometer is. So this is the size of human being and this is the size of spectrometer. And what you see here is probably it's the 300 megahertz spectrometer that you're looking at. So larger the magnetic field you want, probably the larger size of the magnet you're trying to look at. Currently, the record stands at 1.2 gigahertz. It's not anymore in megahertz. Okay, so now that we have taken a little bit of look at how the magnet should be looking in reality, so let's quickly go to the schematic. Let's quickly go to the schematic and understand what are the different components. As I already mentioned to you guys, we are talking about a superconducting magnet. Superconductivity is actually achieved at very low temperatures, and in this case, it's achieved with the use of liquid helium as the source. So liquid helium can be cooled up to 4 Kelvin, and if you actually boil liquid helium, you can go up to something like 2.2 Kelvin or even lesser actually, and depending upon how much you boil off. Right. So What you see here, so this is the solenoidal magnet, the black thing that you're able to see, and that's actually kept in a helium vessel. So that's where the liquid helium goes. The liquid helium helps keep the superconducting magnet at the desired temperature. And of course, immediately outside the superconducting magnet, as you see, this is liquid helium, trying to show liquid helium here, and there is a separation here which ensures that outside that you also have a liquid nitrogen bath. Okay, so basically, in order to ensure that the helium doesn't boil off very fast, you have another layer which helps the nitrogen be available, because nitrogen gas and therefore liquid nitrogen is cheap. We end up trying to minimize the amount of helium, liquid helium that vaporizes by using a liquid nitrogen that's present right outside. And of course, you have a shield outside which we will of course be standing and doing our experiments. Nowadays, these shields are done in such a way that the magnetic field does not affect the person standing nearby. So generally they look for something called a phi Gauss line, and nowadays it's very, very close to the magnet, so we don't have to worry. But if you're looking at older magnets or still going for an MRI scan, you have to be very careful about the magnets. You should carry nothing that's magnetic.
Initially, in the early classes, we'd said the population dependence on temperature is very low.
Correct?
As in, then why are we trying so hard to keep the equipment at low temperature?
Very good question. We are talking about two different things here. All we are talking about here is to achieve a certain B naught, you are going to very low temperatures. On the other hand, if this is confusing you, whether our sample is also in 4 Kelvin, not really. Your sample is at room temperature, which you will see, which is where the probe comes in once again. If you take a look at the probe, this is actually where they are depicting the sample. And the sample's temperature and the magnet temperature are very different.
This
Okay?
is purely for superconductivity, is it?
That is correct. So the vibration legs that you see around, the huge things that I also marked in the big magnets, is to ensure that any vibrations that might come on a ground are dampened. This is important because when you put the sample in the spectrometer, you should never rest your hands on the magnet, because if you do that, it's going to push the magnet down. And you might wonder, okay, why are you so worried about it when you're not acquiring the data? Is because the moment you start moving the magnet a little bit, helium will start boiling off. The moment you start boiling helium off, more helium will boil off. But the moment the gas comes in, the gas would escape, which is where you have all these vents that are present. These vents are for nitrogen and helium. I think one will be for helium, the two others for nitrogen. Nitrogen will escape in one, and the other will be filling every week. On the other hand, you will also have a helium port where you will insert helium and the helium can exhaust through the other one. Okay, so one has to be very careful handling the instrument. Don't touch things that are not required to be touched. These are the Shim coils that we were talking about. Okay, so these are all electromagnets right around your sample in order to homogenize the field a little better than whatever you get from the main magnet. But even before you have the RT shims, you also have something called cryo shims. Unlike the RT shims, which are managed by the user, that is you and me, the cryo shims are set up when the instrument is initially installed. The engineer who comes installs all this to perfection such that the magnetic field is as homogeneous as possible from the cryo shims itself. And any small changes that come up when you put different samples are taken care by the probe. The RF coil that you see here is the one that transmits and receives the signal. And if you're curious about how big the NMR tube is, we are talking about something like 5 millimeters outer diameter. Inner diameter is like 4.2 millimeters. And you're talking about a 7-inch tube. Okay. And you have 500 microliters of solution. So probably the height is about 3 centimeters that is present there. And the active volume or the active length of the coil is something like 1.5 centimeters. Okay, so we will come to the aspect why is that you need to have more sample than whatever is being acquired later. Once again, it helps in the fact that shims can be better done. So there you go. So that's the RF coil, and you're able to see the sample tube. And in addition, this NMR tube is not dropped as it is. You also have something called a spinner. You can imagine that's the spinner, and your NMR tube will look like this. This is where your sample is, and this is called a spinner. The spinner will have different colors, either this way or this way, and this is where you put the sample in, and you are able to see the spinner depicted here. Okay, and the way you get the sample in and out is by having an airlift. I think the airlift will be shown in the probe section, where you push air and the sample will shuttle in and out of the spectrometer. Spinning also is an aspect which helps you get better shims, similar to the fact that when you have more volumes, you will be able to get better shims. And the magnet, once again, which we saw in a little bit of detail here, is shown here. How does the magnet look? So far, what we have seen is what is the block diagram of NMR spectrometer and how does the magnet look. The magnet has different cryogens in order to ensure that the superconductivity is maintained at a low temperature. And the nitrogen is something which we fill every week. On the other hand, helium is something which we fill every three months or so.
Sir, you said that you need to push air for moving the sample up and down.
Right?
Why do we do so, sir? Because anyway we are putting the sample inside.
That's right.
Why
How
do
will
we...
the sample come out? So think about it. You saw how big the NMR magnet is. So you're talking about something like 2 feet here. See, remember, this is made of glass. First of all, you drop a glass in 2 feet. What's going to happen? Glass is going to shatter on the probe. That's not safe, isn't it?
Yes, sir.
Top of it, after that, how are you going to get it out? So the way you do it is with the help of the airlift.
Yes, I thought while taking the data, we need to push it up and down. That's what I thought.
No. While you see, the airlift is just to get the sample in and it stays there until you push it out. The spinner also needs air to spin. If you apply forces along X and Y, the resultant vector will be along Z, correct? So
Yes.
spinning also works the exact same way. That's how people spin the sample within the NMR tube. This is solution state spinning and you spin at something like 20 hertz. Let's say you have little inhomogeneous magnetic field that are present. If you keep on spinning, all the imperfections that are present in the X and Y, if you spin along the Z axis, all the imperfections that are present along the X and Y will get averaged out and you'll get better shims. And that's why you spin the sample along the Z axis at about 10 to 20 hertz. Okay.
Okay, sir.
So the airlift is definitely required. So never ever put the sample without the spinner. Spinner is extremely crucial because that is what helps the airlift push the sample out. If you don't have the spinner, the air will escape and your sample will always remain inside. So that's a problem. Spinner is utmost required whenever you put a sample in. And at the same time, make sure you lift the sample, meaning that in the software you end up using, you will have to type a command which will eject the previous sample and then you have to insert the next sample by carefully removing whatever was inside and putting the next one inside it.
So what is the main difference between solid state NMR and solution state NMR? Is it based on the probe that we are using in both?
Lot of differences, except for the magnet. Even the magnet, the way the bore is present, wherever the bore is where your probe goes in. Okay. Generally, solid state NMR spectrometers have something called a wide bore because their probes are very different in size from solution state. So that is one of the main differences, but there are even more differences that come up. In a solution state NMR experiment, your sample is in the liquid state. And in a solid state NMR, you're going to have powders or crystals that you end up analyzing. The way you are able to nicely take a sample and put it in, solid state NMR is not like that. You will have something called a rotor where you will have a small hole at a certain angle. You will actually put the sample inside it and pack the rotor. Then you take the rotor, put it in. So these are huge differences that come up. And one of the major differences that come up is the angle at which the sample is present. In NMR, the sample is present parallel to the B naught. In solid state NMR, it is present at a 54.7 degree angle. And then what we do is that we spin the sample at say 20 kilohertz. There's a huge difference between this and this. If at all anything for 1D NMR, we spin at 20 hertz. For biomolecular NMR, we don't spin at all. We'll talk about the reason later. But for the solid state NMR, you spin at a very high speed, which is why solid state NMR is associated with almost always called MAS, magic angle spinning, solid state NMR spectroscopy. And generally they are attributed with the spinning speed. In this case, I get 20 kilohertz. There are nowadays rotors that can go up to 100 kilohertz. Solution state NMR predominantly is driven by proton detection. On the other hand, solid state is driven by carbon and nitrogen detection. Nowadays, opposite things are happening, meaning that solution state is going towards carbon and nitrogen and solid state is coming towards proton. Okay, they're trying to meet on a common point. But generally, one can assume that we end up doing proton detection in solution state and carbon nitrogen detection in a solid state. These are very minimal differences that I have pointed out, but these are very critical differences. I hope this answers some of your questions.
Yes, sir. Thank you, sir.